This is going to be the first of the two lessons we scheduled about the fundamental of the surface EMG signal processing by means of our BTS EMG-Analyzer application. Well, we will start now with a very brief introduction about what is the surface EMG and about the main information that are commonly extracted from the analysis of the signals. On the first lesson, in particular, we will talk about algorithms to extract amplitude information, in particular about the full wave rectification and the smoothing or envelope algorithm. Then we will talk also about time and amplitude normalization of the signal. So, what is the surface EMG? As it has been written by Professor Basmajan and De Luca, we can say that the surface EMG is the study of the muscle function through the analysis of the electrical signals originated from the muscular contraction. But we will not go into more details about that now. Actually, our interest is about the functional dynamic surface EMG, that is a non-invasive technique to study about the neuromuscular activation of muscle during a movement task, basically during posture, functional movement, work condition, treatment, and training exercises or other. This is widely used in a lot of application fields for medical research, in orthopedic field, surgery, functional neurology, or gait and posture analysis, or in rehabilitation for post-surgery or accident treatment evaluation, neurological rehabilitation, physical therapy, active training therapy, and so on. Other fields of application are also about ergonomy, mainly, for example, for the risk prevention analysis and for the ergonomic design, for example, or in the sport science field for the athlete training and rehabilitation or injury prevention. By measuring the EMG signal in general, we can extract different information. For example, we can understand if the muscle is active or not during a specific task execution. We can also understand if the muscle is more or less active in one condition respect to another condition, or if the muscle of one side are more or less active compared to the ones of the opposite side. And then, as we consider the EMG during a movement, we can understand when the muscle is on or off in the different phases of the movement. Then, we can try to extract the information about, for example, how much the muscle is active. And in some cases, we can also evaluate about the muscle fatigue. So we will learn during these two sessions about that. After having detected and recorded the electrical activity of the signal, after having recorded the activity coming from the muscle during the contraction, we can investigate about muscle function. To do that, we usually start from the raw EMG signal, which is properly processed and then presented on a document which reports the desired analysis results. Basically, to extract the desired information from the raw signal recorded, we need to create a protocol. A protocol normally includes the set of muscle to analyze, the way about how to perform the data collection, for example, the type of test, the duration, which are the analysis tasks, and so on. And then we need algorithms for data processing to extract the desired information from the recorded signal. And then we have, at the end, to define how to report the results. All those steps can be easily done by means of the BTS EMG-Analyzer application. The EMG-Analyzer application is a user-friendly software which includes a clinical database. Then there are some tools to create a protocol setup with the muscle maps from where to select the desired muscle. Within the application, it is also possible to record the data with the real-time monitoring of the signal to can check about their quality during the recording. There are a lot of algorithms for EMG data processing, and this is the focus of our session. And there are also proper tools to create a user-defined report. At the end, after you have created your own defined protocol and a report, you can save them as a template and you can reuse them for different times to analyze different trials or different sessions. So, before starting using the EMG Analyzer application, I would like to give you just a very brief introduction about some basic algorithms that are commonly used to process the EMG signals. Starting from the raw EMG signals, sometimes can be useful to extract, for example, amplitude or timing information, or sometimes about frequency analysis information. For example, when we want to understand if the muscle is active or not, we need to extract timing and amplitude information. While to understand if the muscle is more or less active again, we need to extract amplitude information. While if we want to extract information about the muscle fatigue, we have to perform a frequency analysis. So we have a lot of algorithms that can be used in the different situations. So let's start with the EMG amplitude information. The on and off and the more or less characteristic of and other qualitative assessment can directly be derived by a quantitative amplitude analysis. So starting from the raw signal, the full wave rectification, the envelope or the smoothing algorithm, and the other here in the list can be used. The first basic algorithm that I want you to talk about is the full wave rectification. By means of that, all the negative amplitude spikes of the raw EMG signal are converted to positive value. And this is performed beside for an easier reading of the signal, but mainly because the main effect of that is in this way the standard amplitude parameter, like for example mean, peak, or the maximum value or the area, can be applied to the curve. Those parameters, in fact, could not be extracted from the raw signal because due to its nature, we have equal and positive and negative values, and as a consequence of that, its mean value would be always set to 0. So, starting from the rectified signal, the average rectified value, commonly called as the RV value, can be easily, for example, computed as the mean value of the rectified EMG signal over a time t. And this sometimes is used as an amplitude estimator of the signal. So now I'm going to show you how to perform the full wave rectification within this smart analyzer application. So let me start with this example where imagine that we want to rectify the EMG signal 1 that you can see in the figure. All the algorithms available to process the EMG signals are inside this block. You can see that we have a lot. The one that I'm going to use is the rectify track. So select that. You have to type the name of the output. So for example, EMG signal 1, rectified. And then to perform the rectification, you have just to drag and drop the signal into the operator input. And this is the results. Okay. So as you can see now, all the value are positive. The second option that we have is the rectify track around mean. This second operation can be useful if you have a signal like that. So as you can see, in this case, the baseline of the signal is not set to 0, but we have an offset. So to do the rectification about this second signal, if you choose the first option, so if we try to perform if you try to rectify the signal around the 0, as it is in this case, now I want to show you the results that, as you can see here, if you choose this option, you cannot compute correctly the rectification of the signal. So you have to choose in this condition the second option, that is to perform the rectification not around the 0, but around the mean of the signal. Okay. So this is the output, the name of the output. So let me now show you the results. Okay. And so, as you can see now, we have now correctly performed the rectification of the signal. Okay, so this is just to show you the meaning of the second operator available. So now imagine that we want, for example, compute the average of the rectified signal between two events. So we have to define the event first. So we have to select the event operator. Okay, so for example, we can define a start and a stop time event. Okay, so now the input of this block can be the rectified signal, so we can select on the trace the start events and the stop. Okay, and then we can click OK. So now what we can do is we can show the two events on the graph, and if we want, we can, for example, compute the average value of the rectified EMG between these two events. So we can choose, or the maximum, sorry. We can choose to compute the maximum first. So the first input is going to be the rectified signal, the second the start event, and the third the stop event. And so this is the result. As you can see, we have computed now the peak value of the rectified EMG into the time interval. Now we can also compute the mean between the two events. Okay. And again, the input, the first is the rectified signal, the second the start event, and the third the stop. Okay, and now we can also add to the graph also the mean value of the signal. Okay, so this is just an example about the two operators available into the Smart Analyzer application to perform the full wave rectification of the signal. Well, the second algorithm that I want to talk to you about is the envelope, which is used to extract, in general, from the raw signal, the more reproducible shape of the EMG, removing the non-reproducible part of the raw signal. This is useful when you want to compute, for example, the average pattern of the signal between different trials, and in case you want to compare trials belonging to different subjects. Two common algorithms that can be used to perform the enveloping of the signal are the moving average, or the integrated EMG, or the root mean square EMG algorithm. In the moving average, a certain amount of data are averaged based on a user-defined time window. The root mean square is based on the square root calculation and reflects the mean power of the signal, and is the preferred recommendation for smoothing, as it is from Isaac recommendation. Both the algorithms are defined for a certain epoch or time window, and typically the time duration chosen is set to 20 milliseconds for example, fast movement, up to 500 of milliseconds, for example, for slow or almost static activities. In general, the bigger is the time window, the more aggressive is the smoothing results on the signal shape. So let me now show you some example by using the Smart Analyzer application. So in this example, we have two signals. One is from an almost static condition, this signal, and the second is from a movement. So imagine that we want to compute, for example, for the first signal, the root mean square EMG with a time window of, we have a almost static activity, so 300 of milliseconds it could be okay. The first input has to be the signal, and now we have to define the time window So I'm going to choose 300 of milliseconds. And this has to be the second input. So this is the results. As you can see, we have now computed, we have extracted the envelope. For the second signal, I can choose a different time window. For example, I will choose 20 milliseconds, so 0.02 second. Again, we have to select root mean square with mobile window algorithm, and the first input again has to be the raw signal, and the second the duration of the time window. And this is the results. So now I want to show you what happens if you increase the duration of the time window. So let me add a new input, time input. I want to show you the results you can get from a time window of 100 of milliseconds. So 0.1 second, and I want to apply the same root mean square with mobile window algorithm and show you the differences between the two. Again, the input, the raw signal, and the second, the time window. So now we can compare the two. First and the second. So as you can see, we get the smoothing effect is higher because we had increased the time window. So what happens if we increase too much the duration of the time window? So for example, now I'm going to choose to show you the results with a time window that is too high, so it has been set to 1 second. So as you can see now, the blue envelope that we get is not correct because, as you can see, we lost some information. So this is just to remind you that you have to set up properly the duration of the time window when you perform a root mean square algorithm. Okay, so now I want to show you the differences between the root mean square algorithm and the integrated EMG. That is another algorithm available into the EMG blocks operator. So I want to show you, I want to compute the algorithm with the same time window of 100 of milliseconds we have chosen for the root mean square algorithm. And so in these graphs you can see the difference between the two algorithms. So we got a signal with a similar shape, with the same shape, but the integration reduces the amplitude of the signal more than the root mean square algorithm. So this is also why it is the preferred algorithm to perform the smoothing or the computation of the envelope of the signal. Well, what about the averaging of the signal? As I have already told you, to describe the typical movement of a signal, we usually analyze a lot of repetition, and we compute the average curve between multiple of them. The averaging required the enveloping, as already discussed, and required also to perform a time normalization on the signal. To do that, it is necessary to define some time events, to define the cycle of the movement, and it is also necessary to identify the phases and the subphases in cases. So, as it can be, for example, the case of the gate analysis, where we define the gate cycle between each heel strike as the one represented by the vertical line on the image, you can see on the image, and the foot-off events, for example, that on the image are represented by the dashed vertical line. These two events define the phases and the subphase of the stance, for example, respect to the total gate cycle duration. So, after performing the time normalization, as you can see, the original millisecond or second time scale is converted to percent of the cycle. So we got a scaling that starts from 0 up to 100. So now I'm going to show you how you can perform time normalization of a signal in a cyclical movement into our EMG analyzer application. So in this example, we have a series of repetition. So as you can see, imagine that we want to extract the pattern of the signal during each sequence. So again, I can compute the root mean square of the signal. Also for this signal, I want to choose a time window of 300 of milliseconds, as we did before. So 0.3 seconds, the second input, and that is the results. Okay, so this is the envelope of the signal. To perform the time normalization, we need to define some events. So we can choose this operator, event sequence on one object, to identify the time events. Okay, and for example, we can choose as events the time peak of the signal that are represented by those vertical lines. So now we can compute the time normalization, the signal normalized with respect to the duration of the cycle. So we can choose the even defined cycles operator, root mean square cycles, where the two inputs are the first, the envelope of the signal, and the second, the sequence of events. So now, as you can see, we have computed the normalized signals for the different cycles we have identified by the events. So from the maximum to the maximum of the signal. And now we can also compute the mean cycles. So we can select cycle sequence mean. And the input, in this case, are all the normalized, all the different cycles. And so in the graphs you can see the results about the computation of the mean cycle and its standard deviation. So in this case, as you can see, in this scale, we changed the time scale from time, so from seconds to 100%, from 0 to 100%. Okay? So now we will talk about amplitude normalization. To perform the quantification of the myoelectric signal comparison that we can make among muscle, among different subjects and different tasks, we can use a normalization procedure. We can to perform the normalization, we can use as a reference value, for example, or one single value, as it can be, for example, the internal peak value or the internal mean value. Otherwise, we can consider, for example, the EMG level of a certain specific task as a reference activity, and the most common method that we know about normalization is to use the isometric maximal voluntary contraction. But we will discuss about that on the next lesson. Also, when you perform the amplitude normalization, you get that the myoelectric values that you get are expressed as percentage of this value. So as you can see, this time of algorithm doesn't change the shape of the EMG curves, but only the Y scaling. So let me now show you also an example about that. So this is the signal that we want to normalize. The first thing again is to compute the root mean square, so to compute the envelope again with the same algorithm. And also in this case I'm going to choose a time window of 300 of milliseconds. So we have to define the time window input. Okay, and now I can show you the results. So imagine now that, for example, we want to normalize the envelope of the signal respect to the peak value, so respect to the maximum. So now we can compute the maximum. As first we have to identify the events, the time events which correspond to the instant when we have the maximum of the signal. So this is the peak. And now we can choose this operator that is under the event operator, even defined value, to define the value of the peak. Okay, so the input is the envelope of the signal and the event the second. So this is the value of the peak. So now if we want to perform the normalization, we can choose the scalar and the operator ratio between two objects. Okay, where the two inputs are the first the root mean square of the signal and the second the peak value. And then if we want to get the value expand to 100%. Okay, so now we can multiply the results by 100. Can you hear me? Can you hear me? Non vedo il microfono. Can you hear me now? Okay, so I don't know if you have been able to hear all the last example. So I don't know if you want that I repeat or not. Okay. Okay, so I'm going to repeat. Give me just... Okay. So this is the example about how to perform the amplitude normalization of the signal. So this is the EMG signal that we want to normalize, to analyze. So we can start with the computation of the root mean square of the signal to compute the envelope. Also in this case I'm going to choose a time window of 300 of milliseconds. So we have to define again the time window, and I'm going to set the time window to 0.3 seconds. Okay, and that is the results. So now imagine that we want to perform the amplitude normalization respect, for example, to the peak value of the envelope of the signal. So to do that, we can identify the events where we have the maximum of the signal, the maximum amplitude of the signal, okay, we can identify the events on the trace. Okay, so that is the case. And now we can compute the value in correspondence of that events. So we can choose event operator and event defined value. So the first input is the envelope of the signal, and the second is the events, which represent the peak time. So that is the peak value. So now if we want to perform the normalization of the signal, we can go into scalar and choose ratio between two events operator. Okay, so now we can divide the envelope of the signal with the peak value. And if we want to get a percentage value, we have to multiply for 100. So we have to define a scalar input of 100, and now we can perform the multiplication between the two objects. So we can now multiply the two scalar value. The division plus 100 for 100, and that is the results. So now, as you can see, we have changed the scale amplitude of the y-axis from 0 to 100 up to 100.